Okay, so the why is it more difficult to jump higher? Got more mass. Any of you still remember who Kareem Abdul-Jabbar was? He just wrote a great book. I'd like to read about he and his relationship with his coach at UCLA, John Wooden, who won. Who while he's at UC, this is a stat that will never ever be broken again. One, because the dynamics of college basketball have changed completely from when John Wooden was at UCLA. They won 88 basketball games in a row. 88 basketball games in a row. They won 10 out of 11 national championships. Now, how did they do that? There weren't any scholarship caps. And John Wooden would just go out, into the playgrounds of New York City and Los Angeles and just recruit all the kids he possibly could, put them all on scholarship. He had all this Hollywood money. And some of the kids who never even got to play still played, wound up in the pros. All they had to say, yeah, I was bench warming for UCLA. Boom. Anyway, so and they also got to play quite a bit because they so remember potential energy. Anyway, I'm losing. It's late Friday afternoon. I'm kind of losing my train of thoughts here. So let's just stay on the let's just focus on the lesson here. Um, this energy comes from work is equal to force times distance. Okay, because here's our force times our distance. And so, how much energy is used up to move a 100-pound person up 50 inches? Well, it's about 200 pounds, is about 91 kilograms. 50 inches is about 1.27 meters. And so that's 1,133 joules, about 0.27 calories. Okay. But it's more difficult because the force, the mass is greater. It takes more energy. It takes more energy to lift with the pads. How much power is generated in the previous jump? Okay, once again, somebody sent me an email, said they were having issues with power. But basically all it is the energy divided by the time. And so that's 11,000 watts. 11,000, that's a lot. That's a lot. Okay. For a brief time, his power output is about the same as 113 100-watt light bulbs. That's a lot, just for that brief period of time. Okay, now, here's what we're doing. Here's a key thing of the whole of what we're doing in this for this lesson. Okay, I should probably stop here, but I'm not going to. I'm gonna kind of press on. So how quickly will somebody come down? Now, this whole idea right now depends on the energy before is equal to the energy after. All right, so we got this diver. He's up here. All right, we're using that red dot as the center of mass. Okay, and so he's going to come jumping down here. His center of mass is going to go from here down to here. So he's going to change his potential energy, his gravitational potential energy, and it's going to equal all kinetic at the bottom. All right, and I want to show you what that looks like when we write it out. So again, let's take this high diver at 10 meters. UG is equal to mgh. Now this energy before is going to equal the energy after, the 1/2 mv squared, the kinetic energy. In other words, he is going to turn all of his potential energy into kinetic energy if there's no friction, which is not here on this earth, but it will. If there is no air resistance, there's no air resistance whatsoever. Then the energy is conserved. We're going to neglect the air resistance, okay? And so basically all we're doing is setting up this equation to find the velocity when he hits the ground. So let's do the algebra real quick before I show you the slide for it. So if we've got mgh is equal to 1/2 mv squared. Now don't want to lose you here. If I have m's on both sides, we can divide both sides by m. That's nice. So we cancel that and that. We get gh is equal to 1/2 times v squared. What I'm solving for is v here. Well, let's multiply both sides by 2 then. So that goes away. You got 2gh is equal to v squared now. And so how do I get rid of the v squared? Take square root of both sides. And if I take the square root of v squared, I get v. So the velocity at the bottom is equal to 2gh. You take the square root of it. All right, so let's see how they solve that. No frictional loss. Conservation of energy means the energy at the top equals the energy at the bottom. Cancel the masses. Independent of mass. So the velocity at the bottom is independent of the mass. It doesn't matter. 14. And so he's going to be going 14 meters per second at the bottom. Okay, go ahead and watch that hammer and feather drop. It's pretty cool. And we're going to stop here.